Dr. Phys here on the rotation matrix, an extremely important concept in theoretical physics. It's used virtually in all branches of physics and in areas of engineering and in areas outside of physics. What we're looking at here is an x and y axes, a Cartesian coordinate system, x and y axes perpendicular to each other, and we're going to rotate x and y by an angle theta. So as x moves up to x prime through angle theta, y goes to y prime through angle theta. So this angle here is also theta. And the point P we're going to look at from 2 points of view in terms of x and y and in terms of x prime and y prime. You might think of x and y as English and x prime and y prime is French, and we want a translation, a dictionary, to go from one set of coordinates to the other. Well, to get the x and y, we do the standard drop down here perpendicular to the x-axis, and when we hit the x-axis with this 90-degree angle, we just pick off our x. That's our x, and our drop down distance here parallel to our y-axis is our y. Now I want to point out that these angles here are actually the same. These two are theta, and you can see that by similar triangles. Here you have a right angle, here you have a right angle, and these two angles here are opposite. Two lines cross, so they're the same, which means the third angle in each triangle must be equal, and you have similar triangles. This angle here, a right triangle, and this angle here, a right triangle, the right angles being here and there, these two angles being the same, and therefore these must be theta. I had a physics teacher many years ago that said if you were to collapse this down by rotating back, this would collapse to 0. You rotate this down, and this here would collapse to 0, so the angles are the same. Well, that's not a mathematical proof. The mathematical proof involves these similar triangles, but you know these angles are going to be either the same or complementary, and to help keep it straight, that's not a bad way to remember it. You simply rotate back, this angle goes to 0, and this thing closes out. Now, to get the x prime and y prime, we use the same idea. We come here parallel to the y prime axis, dropping perpendicular down to x prime, and there's our x prime, longer than our x, and our y prime is simply the drop down from point P to the x prime axis, parallel, see here, to the y prime axis, and that y prime is smaller than our y. Now, the secret here in making the translation is to draw a cute little rectangle in here. This cute little rectangle is drawn by extending this dotted line down, and from the point X coming up parallel to that line, so you hit the x prime axis making a 90-degree angle, and then connect the bottom here parallel to the x prime axis, so you have a nice little rectangle. That is the secret. So now we can do the translation. If we want to look at x prime, it's a long distance here. Look at that. We have to go from the point 0, the origin, up to here, and then add a piece. Well, what is this first part? This first part is x times the cosine of theta. That's that first part. Here it is. And the other part here, this piece here, we're going to pick off by looking at the opposite side of the rectangle, because there we can see it's easily your y times your sine of theta. And we got the x prime. X prime is x cosine theta to get this part here, and y sine theta. For the y prime, we're going to look at the longer distance here and subtract off a piece of our rectangle. This longer distance here is y times the cosine of theta. Here we have it. And we want to subtract this little piece off, which we're going to pick off by the opposite side here, which is easy then to see that that is your x times your sine of theta. And there you have it. Now we would like to put the x first and the y second, so we simply write this one down the same. X is first, y is second. Here, y is first, so we're going to put the y second and put the minus x sine of theta first. And then we define a matrix where we take out the x's and y's and just have the angle part, the trigonometric functions, cosines and sines. And when we then multiply this matrix with the column matrix x and y, we will get our result. In other words, we take these two here, cosine, sine, terms sideways, smack them against here. You have x cosine theta plus y sine theta. There you have it. And then for the y prime, you take these terms sideways and smack them against here. So it's minus sine of theta times x, which is this one, plus cosine of theta times y. and you have a nice elegant way to express our translation from the x and y to the x prime y prime. And here this r of theta is a way of writing the matrix here, and the detailed calculation that I showed you is worked out from the right side.
Now the way to hold these whips is to put that ball, the knot on the end, goes into the palm of your hand and it acts like a swivel. Don't hang on to your whip up here, you hang on to it like this. It goes into your palm of your hand like a swivel. Now just take it easy with these whips, don't try too hard. Now a common mistake that a lot of people make when they try to crack a whip is they go like this. Now if you go like that, what's going to happen is that it will come back, hit you behind the ear, and will cause you a great deal of pain. Now I'll show you this circus crack. It's a very easy crack. There's no shoulder muscle put into it. It's just virtually done with the wrist. And that's all it is. Straight up, straight down, like that. See that? Nice and easy. Give you a side view. It's there. See how the whip rolls out. And when you first do these types of cracks, just do them easily. If you don't get much of a crack, it's not a big bother. Then you can put a bit more effort into it. Get a nice loud crack. There it is, just there. Wrist. See that? No shoulder movement, or no shoulder action. Just the elbow to the wrist.